In order to extrapolate the data to determine whether we have a linear function, quadratic function, or exponential function when given a table of values, we first need to type this data into Desmos. Let's begin with the first data table. So looking at the first data table on Desmos, we're going to click on Table, and from there, we will then enter the data in. I have 0 for x, 1, 2, 3, 4, 5, and 6 for the x's. For the y values, I have 2.2, I have 2.8, I have 3.4, I have 4, I have 4.6, and 5.2, and finally 5.8. From there, looking at this data, I can clearly see right here that this data represents a linear function. So we're going to form a linear regression equation. So we have y1 tilde right here, mx1 plus b. Now looking at this, you can clearly see that the linear regression equation captures the majority of the points. Keep in mind that regression equations are not fully accurate. The values that we picked out from this table of values look very nice and they're very uniform on the line. But the majority of the questions that you guys will get on multiple choices for exams will be a little bit off. Some point here or there might be a few inches above or so on. So looking at the parameters, we have the slope to be 0.6 and the y-intercept to be 2.2 for the b value. From there, we will then go back to our packet and we will indicate that this data table, the first one that we have, is representative of a linear data set. So we're going to write down linear data. And we're going to write down the linear regression equation, y1 tilde mx1 plus b. And we found the equation to be y is equal to approximately 0.6 x plus 2.2. Now, this linear regression equation will help us determine future values. For example, if I want to identify what the y value will be when x is equal to 10, when x equals 12, when x equals 23, and so on, I'm able to give a good approximation. Again, keep in mind that this is an approximation, a good estimate, a good best fits model. It is not fully accurate, okay? Moving on to the second data table, we have to determine, again, whether this data represents a linear function, quadratic function, or perhaps an exponential function. So let's go ahead and type it into Desmos. Keep in mind that when you're typing this into Desmos or your TI-84, you need to delete the data to ensure that you do not make a mistake. So let's go ahead and type in our table of values. We have 0, we have 1, 2, 3, 4, 5, 6. And for the y values, I have 0.6 for the y-intercept. I have 1.2. I have 2.4. I have 4.8. I have 9.6. I have 19.2. And finally, I have 38.4. Now, looking at this data, I'm just going to zoom out just a little bit. I can clearly see right here that this data will be a good representation of an exponential function. And just to ensure that I'm correct about that idea, I am going to type in the regression equation for the exponential function by typing in y1 tilde a, close parentheses, b, close parentheses, to the power of x1. From there, I can see clearly right here that the exponential regression equation will capture the majority of the points. This will ensure that I have an accurate result. Not fully accurate, but a good approximation. From there, I can see that the A value is going to be 0.6. The B value will be positive 2. So from there, I will go back to this paper and I will indicate that the second table of values represents an exponential data set. Let's write that down. Exponential data set. Okay? And I'm going to write down the regression equation. I have y1 tilde a parentheses b to the power of x1. Based on the information that I gathered from the data table, I can indicate that the equation is going to be y equals 0.6 parentheses 2 to the power x, or I can write this down as a fraction. Instead of a decimal of 0.6, I can also say y is equal to 3 over 5 times 2 to the power of x. And that's going to be my exponential regression equation. And this will help me calculate future values. If I want to calculate what will be the y value when x is equal to positive 9, or when x is equal to positive 12, and so on, I'm able to give a good approximation. Again, this is not fully accurate, but it's a good approximation. Finally, for the last data table, I'm going to type this into Desmos. And we have to delete all the previous data to ensure that I have an accurate result. So we're going to type in 0, 1, 2, 3, 4, 5, 6. And for the y values, we will type in 1.2 for the y-intercept. We're going to type in 2.6, 6.8, 13.8, 23.6, 36.2, and 51.6. From there, I can zoom out and I will see that this data looks very similar to a quadratic regression equation. Now, if you're a little bit confused, how does this look like that? Well, we can go ahead and verify this. So let's type in the quadratic regression equation, y1 tilde a x1 square plus b x1 plus c. And looking at this visual representation, we can clearly see that the quadratic regression equation captures the majority of the points right here. Now, again, keep in mind that the data that we have out there is not fully accurate. And to some extent, some of these points are a little bit off, okay? Hi there. So from there, we will then write this equation onto our document. So this data table represents a quadratic data set. Let's write that down. Quadratic data. And the quadratic regression equation is given to us by y1 tilde a x1 square plus bx1 plus c. From there, we will then grab the parameters that we found on the Desmos, on the TI-84. And we saw that we can form the following equation. Y is equal to 1.4 x squared plus 0x plus 1.2. Or I can rewrite this to be what? Y equals 1.4 x squared plus 1.2. We do not need to write down the 0x. So let's go ahead and box this right here. So this is my quadratic regression equation, which can help me identify and approximate a good value when x is equal to 13, when x equals 25, or whatever I need. From there, let's go ahead and see a multiple choice question that's very similar to a good chunk of exams that have this idea. Let's read it. A cup of soup is left on a countertop to cool. The table below gives the temperatures in degrees Fahrenheit of the soup recorded over a 10-minute period. Write an exponential regression equation for the data, rounding all values to the nearest thousandths place, So let's go ahead and box the vocab word exponential regression equation. So if we see that vocab word, we know automatically that we're going to use the following regression equation. Y1 tilde a parentheses b to the power x1. Then I am going to round to the nearest thousandths place, which is what? Just in case you forgot, let's go ahead and write this down. So the first digit after the decimal point is the tenths place, okay? So let's go ahead and just label that really quickly. This is the tenths place, okay? Then the second digit is the hundredths place, okay? And I'm just quickly writing them. If I misspell it, that's my apologies, okay? And then finally, the third digit after the decimal point represents the thousandths place. In this case, this is what I'm looking for. Now, keep in mind that the number next to this term if it's 5 or more, you add 1 to that previous number. If it's less than 5, you cut it off. All right. Now, just to make your life a little bit easier, I was able to type this information onto Desmos prior to this, or my TI-84. And I found that the parameters are the following. My A value, when rounded to the nearest thousandths place, is going to be approximately 180.377. My B value is going to be approximately, when rounded to the nearest thousandths place, 0.954. From there, I will then substitute this information onto the regression equation that I have. So I have y equals 180.377 parentheses 0.954 to the x power. There we go. And that's my exponential regression equation. Now, what does this help us do? Well, this equation helps us identify the temperature of the soup within any time frame. So if I want to calculate the temperature of the soup within 15 minutes, I can do that. Or if I want to calculate the temperature of the soup within 25 minutes, I can do that as well. So actually, let's go ahead and write down a quick question about that. Let's go ahead and say that I want to predict the temperature, let's write down temp, of the soup after 15 minutes. Let's just go ahead and say that. Let's write that question down. We might see this on the test, okay? Or in any future test that you might have. So in this case scenario, keep in mind that we have already found the regression equation for the data right there for all future temperatures of the soup, okay? So what can I say? Well, I can go ahead and say that x is equal to 15, right? All right. And we're going to substitute this into the regression equation that we found. So I have y equals 180.377, that remains the same, parentheses 0.954, that remains the same. But instead of x, we now can substitute 15. And if you type this into the calculator and you round to the nearest thousandths place, you will end up with y is approximately 89.003 degrees Fahrenheit. So what does that mean for us? Well, it means that the temperature of the soup after 15 minutes is going to be approximately 89 degrees Fahrenheit. But if you want to be more direct about this in terms of the thousandths place, it's going to be 89.003 degrees Fahrenheit.